Let's start with a simple introduction. Artificial intelligence, often called AI, is a field of computer science dedicated to creating smart machines. These machines are designed to perform tasks that usually require human intelligence. Think about how you recognize a friend's face in a photo, understand what someone is saying, or make a decision about the best route to take to the store. AI aims to give computers these same abilities. For instance, when you use a navigation app on your phone, it uses AI to find the quickest path, considering traffic and road closures. This is a practical example of AI helping you solve a real-world problem, much like a human would, but often much faster and with more data. Everyday examples of AI are all around us, even if we do not always notice them. When you unlock your smartphone with your face, that is AI at work, using facial recognition technology to identify you. When you get recommendations for movies or shows on a streaming service, an AI system has analyzed your viewing history to suggest things you might enjoy. Even the spam filter in your email inbox is a form of AI, learning to distinguish between important messages and unwanted advertisements. These systems are not just following pre-written instructions, they are adapting and making intelligent choices based on the information they receive, making our lives more convenient and efficient in countless small ways. The core idea behind all these examples is that AI enables a machine to perceive its environment and take actions to achieve a specific goal. This is a very broad definition, and it covers a wide range of technologies and methods. Some AI systems are relatively simple, designed for one specific task, like playing a game of chess. Others are much more complex, aiming to replicate human-like understanding and reasoning across many different domains. The ultimate ambition of many researchers in the field is to create what is known as Artificial General Intelligence, or AGI, a system with the same broad, flexible intelligence as a human being. We are still a long way from that goal, but the progress we have made so far is truly remarkable. So, in simple terms, AI is about building systems that can think, learn, and act intelligently. It is not about creating robots that look and act exactly like humans in every way, as often depicted in science fiction. Instead, it is about creating useful tools that can augment our own intelligence and help us solve some of the world's most challenging problems. From helping doctors diagnose diseases earlier to managing complex energy grids, AI is becoming an essential part of modern life. Understanding the basic principles of what AI is and how it works is the first step toward appreciating its incredible potential and navigating its development responsibly. It is a journey into creating intelligence itself. To truly understand artificial intelligence, it is helpful to look at the different goals researchers have pursued over the years. We can organize these goals into 4 distinct categories, which I often refer to as the 4 pillars of AI. These categories are based on 2 dimensions, whether the focus is on thinking or behavior, and whether the goal is to mimic humans or to achieve perfect rationality. The first category is thinking humanly. This approach, often associated with cognitive science, seeks to build machines that think like people. It involves understanding the inner workings of the human mind, how we form thoughts, memories, and beliefs, and then trying to create computational models that replicate those processes. The second category is acting humanly. This is the focus of the famous Turing test, proposed by Alan Turing. In this test, a human interrogator tries to distinguish between a human and a computer based on their typed responses to questions. If the computer can fool the interrogator into believing it is human, it is said to have passed the test. This approach is less concerned with whether the machine's internal thought processes are human-like. It only cares about whether its external behavior is indistinguishable from a human's. Early chatbots and natural language processing systems were often developed with this goal in mind, aiming to create a convincing human-like conversation partner. The third perspective shifts the focus from humans to an ideal standard of intelligence rationality. This brings us to thinking rationally, also known as the laws of thought approach. This tradition dates back to the philosopher Aristotle, who tried to codify right thinking, unbeatable patterns of reasoning. The idea is to build systems that use logic and formal reasoning to make deductions and draw correct conclusions. For example, if we tell a system that all humans are mortal and Socrates is a human, a rationally thinking system should be able to conclude with certainty that Socrates is mortal. This approach is foundational to many areas of AI, especially in systems where provably correct reasoning is critical. Finally, we have the fourth category, acting rationally. This is the approach that my co-author Peter Norvig and I emphasize in our work. A rational agent is one that acts to achieve the best possible outcome, or, when there is uncertainty, the best expected outcome. It is not necessarily about thinking like a human or thinking in pure logic, but about doing the right thing. For example, a self-driving car that brakes to avoid an obstacle is acting rationally. It doesn't need to feel fear or reason about mortality, it simply needs to take the action that best ensures its primary goal of safe transportation. This perspective is powerful because it is more general and provides a clear way to design and evaluate AI systems based on their performance in the real world. To bring the ideas of artificial intelligence to life, we need a language to communicate our instructions to a computer. For many developers and researchers in the AI field, the language of choice is Python. Python is a high-level programming language known for its simple, clean syntax that is relatively easy for beginners to learn. Its readability means that you can write code that looks a lot like plain English, which makes it easier to focus on the complex logic of AI rather than getting bogged down by complicated programming rules. This simplicity does not come at the cost of power. Python is incredibly versatile and supports the development of everything from simple scripts to large-scale, complex AI applications. What truly makes Python the dominant language for AI is its extensive ecosystem of libraries. A library is a collection of pre-written code that provides ready-to-use functions and tools for specific tasks. Instead of having to write everything from scratch, you can import a library and immediately gain access to powerful capabilities. For artificial intelligence, a few libraries are absolutely essential. One of the most fundamental is NumPy, which stands for Numerical Python. NumPy provides powerful tools for working with large multi-dimensional arrays and matrices, which are the primary data structures used to represent everything from images to text in AI models. It is the bedrock for most scientific computing in Python. Building upon NumPy, we have Pandas, a library designed for data manipulation and analysis. In any AI project, a significant amount of time is spent cleaning, organizing, and preparing data. Pandas makes this process much more manageable with its flexible data structures, particularly the data frame, which is like a powerful spreadsheet you can control with code. To understand your data, you need to visualize it, and that is where Matplotlib comes in. It is a plotting library that allows you to create a wide variety of static, animated, and interactive charts and graphs, helping you spot trends, patterns, and outliers in your data before you even start building an AI model. For machine learning specifically, the scikit-learn library is an indispensable tool. It provides simple and efficient tools for data mining and data analysis, offering a wide range of algorithms for classification, regression, clustering, and more, all with a consistent and easy-to-use interface. When you're ready to move into deep learning, which involves building complex neural networks, libraries like TensorFlow and PyTorch become essential. These frameworks provide the building blocks for creating and training sophisticated models that power everything from image recognition to natural language understanding. Mastering these libraries is key to becoming a proficient AI practitioner, as they provide the powerful toolkit you need to build intelligent systems. At its core, many problems in artificial intelligence can be framed as a search for a solution. Imagine you are trying to solve a Rubik's Cube. You start from a scrambled state and want to reach the solved state. Every twist you make is a step, and you are essentially searching through a massive space of possible configurations to find the sequence of twists that leads to the goal. This is exactly how an AI can approach problem solving. It defines a problem in terms of an initial state, a set of possible actions, and a goal test that determines if a state is a solution. The process of finding the sequence of actions that leads from the initial state to a goal state is called search. There are many different strategies or algorithms for conducting this search, each with its own strengths and weaknesses. One of the simplest is called breadth-first search, or BFS. Think of this like exploring a maze by first checking every path that is one turn away, then every path that is 2 turns away, and so on. You explore layer by layer, guaranteeing that you will find the shortest path to the exit, assuming one exists. This is useful when the cost of each step is the same, like in our Rubik's Cube example where each twist counts as one move. The downside is that it can consume a lot of memory, as it needs to keep track of all the paths at the current layer of exploration. Another fundamental strategy is depth-first search, or DFS. In our maze analogy, this is like picking one path and following it as deep as you can go until you hit a dead end. If you hit a dead end, you backtrack to the last junction and try a different path. This approach uses much less memory than BFS because it only needs to remember the single path it is currently exploring. However, it does not guarantee finding the shortest path. It might wander down a very long, inefficient route before finding a solution, or even get stuck in an infinite loop if the search space is not finite. The choice between BFS and DFS often depends on the nature of the problem and the resources available. Of course, we can do better than just blindly exploring. This is where informed or heuristic search algorithms come in. A heuristic is a rule of thumb or an educated guess that helps guide the search toward the most promising states. An excellent example is the A** search algorithm. A* combines the benefits of finding the shortest path, like BFS, with the guidance of a heuristic. For a navigation app, the heuristic might be the straight-line distance to the destination. A* will prioritize exploring roads that not only have a low travel cost so far, but also seem to be heading in the right direction. This intelligent guidance allows it to find the optimal solution much more efficiently than uninformed methods, making it a cornerstone of problem-solving in AI. Machine learning is a subfield of artificial intelligence that gives computers the ability to learn without being explicitly programmed for every single task. Instead of writing detailed step-by-step instructions, we provide the computer with a large amount of data and an algorithm that allows it to learn patterns from that data. Arthur Samuel, a pioneer in AI, described it as the field of study that gives computers the ability to learn without being explicitly programmed. Think of it like teaching a child to recognize a cat. You don't describe a cat with a set of logical rules. You show them many pictures of cats, and eventually, they learn to identify a cat on their own. Machine learning works in a very similar way. There are three main types of machine learning, each defined by the kind of data and feedback it uses to learn. The most common type is supervised learning. In this approach, the machine is trained on a dataset where the right answers are already known. For example, to train an email spam detector, we would feed it thousands of emails that have been pre-labeled as either spam or not spam. The algorithm learns the features that are associated with each label, like certain keywords or sender addresses. Once trained, it can then predict whether a new unlabeled email is spam. Other common tasks for supervised learning include predicting house prices based on features like size and location. The second type is unsupervised learning. Here, the algorithm is given data that has not been labeled or categorized. The goal is not to predict a specific outcome, but to find hidden structures or patterns within the data itself. For example, a company might use unsupervised learning to analyze its customer data and discover distinct groups or segments of customers with similar purchasing habits. This can help in creating targeted marketing campaigns. Another application is anomaly detection, where the algorithm learns what normal data looks like and can then flag any unusual data points that might indicate fraud or a system error. The machine learns to organize the information without any predefined labels. The third type is reinforcement learning. This is all about learning through trial and error, much like how an animal learns a new trick. An AI agent is placed in an environment and learns to make decisions by performing actions and receiving rewards or penalties. For instance, to train an AI to play a video game, the agent would receive a positive reward for scoring points and a negative reward for losing a life. Over many attempts, the agent learns a strategy or policy that maximizes its total reward over time. This powerful approach is behind the AI systems that have mastered complex games like Go and chess, and it is also being used to control robots and optimize complex logistical systems. Section 6. Grouping and sorting: the magic of clustering. Clustering is a fundamental technique within the world of unsupervised machine learning. Its primary goal is to take a collection of data points and group them into clusters based on their similarities. The key idea is that items within the same cluster should be very similar to each other, while items in different clusters should be quite distinct. Imagine you have a large box of mixed fruits. Without knowing the names of the fruits, you could still start sorting them. You would likely put all the red round items together, the long yellow items together, and the small purple spheres together. You have just performed clustering. You created groups based on shared characteristics like color, shape, and size. This process of automatically identifying natural groupings in data is incredibly useful across many different fields. For example, in biology, scientists can use clustering to group genes that have similar expression patterns, which might suggest they share a common function or are involved in the same biological processes. In marketing, as mentioned before, clustering can segment customers into distinct personas based on their demographics and buying behavior. This allows businesses to move beyond a one-size-fits-all approach and tailor their products and messages to the specific needs and preferences of each group, leading to more effective engagement and customer satisfaction. One of the most well-known and widely used clustering algorithms is called K-means. The K in K-means represents the number of clusters you want to find. The algorithm starts by randomly placing K-central points called centroids within the data. Then it repeats two simple steps. First, it assigns each data point to the nearest centroid, forming K-initial clusters. Second, it recalculates the position of each centroid to be the new center of all the data points assigned to it. These two steps are repeated over and over again until the centroids no longer move, meaning that the clusters have stabilized. The result is a simple and effective partitioning of the data into K distinct groups. The importance of clustering lies in its ability to reveal the underlying structure of data without any prior knowledge or labels. It is a powerful tool for exploration and discovery. By grouping data, we can simplify complex data sets, making them easier to understand and analyze. It can help us identify anomalies that do not fit into any cluster, discover relationships we never knew existed, and provide a solid foundation for more advanced analysis. In a world overflowing with information, clustering provides a way to find order in the chaos, helping us make sense of the vast amounts of data that surround us and turn that data into actionable insights. Section 7. Intelligent Agents AI in Action. At the heart of modern artificial intelligence is the concept of an intelligent agent. An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. A human agent has eyes, ears, and other organs for sensors and hands, legs, and a mouth for actuators. A robotic agent might have cameras and infrared rangefinders for sensors and various motors for actuators. Even a software agent, like a web crawler, perceives its environment and acts upon it. The key is this continuous cycle of perceiving and acting. What makes an agent intelligent is its ability to act rationally. As we discussed earlier, this means it acts to achieve the best possible outcome based on what it perceives and the knowledge it possesses. The agent's behavior is determined by its agent function, which is an abstract mapping from any given sequence of perceptions to an action. For example, the agent function for a vacuum cleaner robot might map a perception of dirt detected to the action suck. The goal is to design an agent program that implements this agent function. The program runs on the physical architecture of the agent, whether that is a robot or a standard computer. There are several basic kinds of agent programs which vary in complexity and intelligence. The simplest is a simple reflex agent. This agent selects actions based only on the current percept, ignoring the rest of the percept history. It operates on simple condition action rules like if the car in front is braking, then initiate braking. A slightly more advanced type is the model-based reflex agent. This agent maintains an internal state, or model, of how the world works. It uses this model to keep track of the parts of the world it cannot see right now, allowing it to make better decisions than a simple reflex agent. For example, it can keep track of where other cars are even if they are temporarily out of sight. Moving up in sophistication, we have goal-based agents and utility-based agents. A goal-based agent thinks ahead. It considers the future consequences of its actions to decide which ones will help it achieve its goals. For instance, a navigation agent needs to know its destination to choose the right turns. A utility-based agent takes this a step further. When there are multiple ways to achieve a goal or multiple conflicting goals, it uses a utility function to choose the action that leads to the best or happiest state. This allows it to make trade-offs, like choosing a slightly longer but safer route. These agent designs provide a powerful framework for building AI systems that can operate autonomously and effectively in complex environments. Section 8. The Physical World. AI's Connection to Robotics. Robotics is the field of engineering and science that deals with the design, construction, operation, and use of robots. When we combine robotics with artificial intelligence, we get intelligent robots, physical agents that can perceive and act upon the world around them. While AI can exist purely in software, like a chatbot or a recommendation engine, robotics gives AI a body to interact with the physical world. This connection allows AI to move beyond the digital realm and perform tasks that require physical manipulation, navigation, and interaction. A factory robot arm, a self-driving car, and a planetary rover are all examples of AI-powered robotics. For a robot to operate intelligently, it must be able to solve several key problems. The first is perception, or sensing the world. Robots use a variety of sensors to gather information. Cameras provide visual data, much like our eyes, allowing the robot to perform tasks like object recognition and scene understanding. LiDAR sensors use laser beams to create detailed three-dimensional maps of the environment, which is crucial for navigation and obstacle avoidance in self-driving cars. Other sensors might include microphones for hearing commands, tactile sensors for feeling pressure, and GPS for determining location. The AI component is responsible for processing this raw sensor data and turning it into a useful understanding of the environment. Once a robot perceives its environment, it needs to act. This involves locomotion and manipulation. Locomotion is the ability to move from one place to another. This could mean using wheels, legs, or even propellers. The AI must plan a path that avoids obstacles and safely reaches the destination. Manipulation is the ability to interact with objects, for example, by picking something up, opening a door, or assembling a part. This requires precise control over motors and grippers, guided by the robot's perception. For instance, a robotic arm in a factory uses computer vision to locate a part, then calculates the exact sequence of joint movements needed to pick it up and place it correctly. The combination of AI and robotics is transforming industries and creating new possibilities. In manufacturing, intelligent robots work alongside humans to assemble products with high speed and precision. In logistics, autonomous robots navigate vast warehouses to sort and transport packages, making e-commerce faster and more efficient. In healthcare, robotic systems can assist surgeons in performing delicate operations with greater accuracy. In exploration, robots like the Mars rovers explore distant worlds that are too dangerous or remote for humans. As AI algorithms become more advanced, the capabilities of these physical agents will continue to grow, allowing them to take on increasingly complex tasks in the real world. Section 9. The human side of AI, navigating ethical challenges. As artificial intelligence becomes more powerful and integrated into our daily lives, it is crucial that we consider the ethical implications of its development and deployment. AI is not just a technical discipline, it is a social one, and the systems we build can have profound impacts on individuals and society. One of the most significant ethical challenges is bias. Machine learning models learn from the data they are given. If that data reflects existing societal biases related to race, gender, or other characteristics, the AI system will learn and often amplify those biases. For example, if a hiring system is trained on historical data from a company that predominantly hired men, it may learn to unfairly penalize female candidates. Another critical issue is fairness and accountability. When an AI system makes a decision that affects a person's life, such as approving a loan, diagnosing a medical condition, or guiding a self-driving car, who is responsible if something goes wrong? Is it the programmer who wrote the code, the company that deployed the system, or the user who operated it? Many complex AI models, particularly deep learning networks, operate as black boxes, making it difficult to understand exactly how they arrived at a particular decision. Ensuring transparency and establishing clear lines of accountability are essential for building trust, and ensuring that these systems are used fairly and responsibly. Privacy is another major concern. AI systems, especially those that power personalized services, often require vast amounts of personal data to function effectively. This data can include everything from your location history and online searches to your private conversations with voice assistants. The collection and use of this data raise important questions about consent, security, and surveillance. We must ensure that strong privacy protections are in place to prevent the misuse of personal information and to give individuals control over their own data. The potential for AI to be used for mass surveillance by governments or corporations is a serious threat to personal freedom that requires careful regulation. Finally, we must confront the impact of AI on jobs and the economy. As AI-powered automation becomes more capable, it has the potential to displace human workers in many industries, from transportation and manufacturing to customer service and data analysis. While new jobs will certainly be created, this transition could lead to significant economic disruption and increase inequality if not managed carefully. This raises fundamental questions about the future of work and our societal values. As we develop this powerful technology, we have a collective responsibility to steer its trajectory towards a future that is not only intelligent and efficient, but also equitable, just, and beneficial for all of humanity.